exponential functions all look like this. Y equals a times b to the x. And we're going to write the equation that passes through these two sets of ordered pairs, 1, 6 and 3, 24. And we have done something similar to this in the past. We wrote equations of polynomials that had those. We had parabolas. We've done lots of different ways of this. Again, you're going to find out this is an extremely easy method. The way that we do this is that we start out by writing out the generic form twice. And now it's just a matter of substituting in for x and y. So, equation on the left, I'm going to get 6 is a times b to the 1. And then on the other side, I'm going to get 24 is a times b cubed. Everybody okay with that?
Yeah.
What we're doing here is we're creating a system of equations, and we're going to solve this via substitution. And whether we're working with the exponent function or the exponent model or the power model here in a minute, we're always want to get a by itself, because a is not going to have an exponent. It's easier to work with. So if I solve the equation on the left for a, I'm going to get 6 divided by b is a. Do you agree? Is it okay that I did not write b to the first power?
Yeah.
So now I have a, I'm going to substitute in here on the other equation. So I'm going to get 24 is 6 divided by b times b cubed. Very good. And what does it become on the right-hand side then? 6b squared. And now we're back to a two-step equation. Divide by 6. And b is? We don't have to write plus or minus with these. All right? We're not going to worry about plus minus in this scenario. Because we're talking about exponent rules, we're not worrying about the plus minus. So now I know what b is. Could I figure out what a is?
3.
How did you do that?
Well, 6 equals a times 2.
So again, what we're doing is substituting back to the original equation, or when we solve
I was
for
the
a.
only one up there. I don't know.
Well, that's fine. And we have, so 6 divided by 2 gives us 3, which is a. So your last step then is to write it in terms of a's and b's. Y equals 3 times 2 to the x. And you're done. Again, when we started working with growth and decay problems, we never multiplied the a and b together. We just left it as a times b to the x. Same reason here. And that's what it looks like. Yes, sir? Yep. That's the equation. It's really not that bad. Okay? It's really not that bad. One thing I want you to notice, I don't know how well you can see this as far as the glare on the board here. There are two different forms of these, the exponent function versus the power function. The only thing that's different between the two, x is the exponent, x is not. So if you remember that x is the exponent for the exponent one, this is just it's just x and b switched. All right, so you don't really have to memorize both of them. You know one of them, the other one is just moving flip-flop. Again, not horribly scary, I'm assuming.
Not horrible at all.
Let me show you the other one. When I'm going the other direction, if I want to write a power function, it looks just a little bit different. This function looks like y equals a times x to the b. And we're going to write, again, we're going to rewrite it in terms of a's and b's, but we're going to solve to figure out the a's and b's again by using substitution. So here we have the ordered pairs, excuse me, of 2, 5, and 6 and 9. So we write them out. Yes, sir.
So it'll let you know when to use the.
Yeah, it'll say write an exponential function, or it'll say write a power function. It'll say one of those two. Bless you. Again, substitute in. I know that 5 is going to equal a times 2 to the b. And I know that 9 is going to equal a times 6 to the b. I want to rewrite one of the equations in terms of a. So just write the first one in terms of a. To get a by itself, I have to divide both sides by 2 to the b. Good. So I'm going to get 5 over 2 to the b is a. And again, what do you think we're going to do with that?
Subs.
Yep. We're going to take this value of a now and substitute back here. I get 9 is 5 over 2 to the b times 6 to the b. Again, the equation on the left, in order to set that up, what's 6b over 2b?
2.
It's 3b.
3b.
So I'm going to get 9 equals 5 times 3b. Now, does everybody agree that we're eventually going to have to take a logarithm here?
Yes.
I agree. What do I have to do first though before I can log?
Divide by 5.
Good, divide by 5. So I'm going to get 9 over 5 is 3 to the b. What's the log base we have to take at both sides then?
3.
Good. So now, in our calculator, I take the log base 3 of 9/5. I get 0.54 for b.
Alright, fair enough.
Which means I take this value and I substitute back there to find a. Again, when you're dealing with the power functions, you're going to have to do logarithms. You're going to have some rounding. Make sure you round to 2 decimal places. So this is going to become 5 over 2 to the 0.54.
Wait, I thought you said that we couldn't enter like the specific logs in the
I showed you guys how to do that. I just didn't show you how to do that with graphing right away because it's just too easy.
Wait, how do you do that again?
Alpha window. Is it alpha window or alpha zoom? Alpha window number 5.
Math alpha math.
Oh, okay. Math, alpha, math.
Easy enough.
And then 3, 4, 4.
Yeah. Found 4.
So now you know what A is, and you know what B is. Put them back together, you're going to get y equals 3.44x to the 0.54. Again, not horribly scary, I'm assuming. I'll take a second and just do one of the power ones tend to be a little bit messier just because you have to deal with the logarithm. The other ones are going to be very straightforward. So let's see here. I think I got another one of those here. Do this one real quick is a power. So it's going to be y equals a times x to the b. Try this one real fast. Let's see how we do.
On the board?
It's called the logistic growth model.
You
On
should
the
fix
board?
that
Now-
on the board.
Can you fix
Can
that
you
on the
fix
board?
that? Can I fix
It looks like a
that?
plot. It looks like a T.
Make it look
I
more
thought it was
like a
like
plus.
E
It looks like
ten.
an
Alright.
H.
Guys, again, this is not going to take very long. I want to make sure that we have a minute to go over some stuff about that quiz. I want to explain to you what these values are and how we work with them. So everything we've dealt with so far has been exponential growth, exponential decay. And the growth or the decay was always constant. It was constantly decaying, constantly growing at a specified rate. It never tailed off. There was, our domains, or excuse me, our ranges were always all real numbers. It didn't have a cap on it. Well, over time, in the real world, you can have growth up to a specific value, and then it's going to continuously approach it. Okay? If you think about population growth eventually will tail off. You know, you just run out of people. You know, you can't constantly build upon build and build.
How's that gonna work?
So what happens here with logistic growth functions is that these graphs, and we're just going to kind of do some rough hand sketching of graphs with some very basic parameters to them. They're all going to kind of look the same. We start out with just an XY grid. That is the generic. This is the generic form.
What is all the stuff in
I'm getting there. All right. There's nothing like a cost. There's not like an initial amount or anything like that. You're going to be given an equation and it's going to say graph it. I'm just going to show you guys how these things plot out with these specific parts here. So what happens now in every growth model, you're going to get two asymptotes. You're always going to have two horizontal asymptotes for these growth models. These growth models, their asymptotes are going to be at, the horizontal asymptotes will always be at y equals 0 and y equals c. Okay? It's always going to happen. All of these graphs look like this. All these graphs look like this. Now, the 2 points that you have to plot is going to be your y-intercept. And the y-intercept is always located at the c value divided by 1 plus the a value. And I'm going to do an example numerically and walk you through it. It's very, very, very simple. That's how you find your y-intercept. Now, also, in a calculator, you can find a y-intercept by pressing y-intercept. You can find the intercepts that way as well. Now, there's also one other point that occurs within these growth models. What happens here is that there's a point here where it's no longer increasing, the rate of increase starts decreasing. It's slowing down. It's starting to slow itself out. All right? And what happens now is that there's an ordered pair here. I want to talk about the range. When I'm talking about the range, is that the x values or the y values?
Y.
Okay. Now, if I'm going to find a halfway point given a range, one thing I want you to notice here is that you always have a bottom asymptote always at 0, and your top asymptote is always going to be at your c value. Where is the halfway point going to be for the y values? What would be a generic way of finding that? Okay? If c is always the top part, 0 is always the bottom, where's the halfway point? Okay, how do I find that algebraically? All right, what's the top one? C. C divided by 2. The y coordinate's always going to be at c over 2. Always, always, always. The x coordinate's the weird one. The x coordinate, we have to use the natural log. You take the natural log of the a value divided by the r value. Again, this is something that will be, obviously you have to use a calculator to find these x and y values. It's not going to be that horrible. So let me show you how this looks with an actual problem. I'm going to walk through all the steps again. If I take this function, and these are basically the three things I'm looking for on these graphs. I have y equals 6 over 1 plus 2e to the negative 0.5x. Now, when we have this out as that negative r value, that means your r value is 0.5. It's always the opposite of it, just like your h's were always opposite signs. Okay? Pretty much they're always going to be, r is always going to be a positive value.
But it's the opposite of
What's that? It's just some, when I took the picture, just don't worry about it.
Oh,
I see nothing. There's nothing to see here. Alright. So again, when I go to sketch this, what's your value of C? 6. So where's your horizontal asymptote? There's a horizontal asymptote at 6, and one down here at 0. So my horizontal asymptotes are at y equals 6 and y equals 0.
So one of them will always be at 0?
Yep, always. Always at 0 and always at C. Now let down a boat at C, but the curves always kind of go like this. Now to find our y-intercept. Very good. The y-intercept is occurring at 6 divided by 1 plus 2. And again, I got that the 6 is the C value, 2 is the A value, just straight out of there. So it's 6 over 3, and I got, or 6 over 3, and it gives me 2. So your y-intercept is at 0, comma 2. And now I have to find this last point. The y value is going to be 3, because it's the halfway point between 0 and 6. And then the last, the x coordinate is just the weird one. Again, use the calculator to find it. It's the natural log of A.
Is there a natural log button?
Yeah, there's an L button. It's right below the log button, I believe, on the left-hand side. And divide that by 0.5. I mean, you can just leave it like that if you want. I really don't care what the decimal is. What's that? No, the R value is always, it's just that decimal. Don't worry about the negative sign. So that's what they call the point of change. It's where it's changing direction.
1.39,
Sure. So it's natural log of 2 over 0.5, comma 3.
Oh, we don't even have to like.
No, I'm not. If you want to press the button, it's not a big deal. But in essence, that's kind of what I want you guys to be able to look at. So again, when we go to graph something like this, it's really, really, really fast. You're going to have an asymptote at your numerator, whatever that is. Your calculators will graph it for you as well. And you can probably find all that information via pressing buttons on the calculator.
So what's the difference?
What's that?
What is C and A?
And I don't know what the actual value, the letter, it's just the letter they gave it. That's all. There's no cost function or anything here. It's just, this is the model. This is what the graph looks like. Yeah. It's the L button is right on your left-hand side. I believe it's right below the log button. All right. Not so scary?
Nope.
Really isn't. Now let me throw the worst thing of today at you. Solve for x.
Okay. I got it.
Is it one of the worst?
Yeah. Which really is each other.
You have another one.
Multiply both sides by 1 plus 10 and
It's only bad if you're a sheep.
Now, one thing I want to show you guys here, a lot of people forget about this little trick. Isn't this just fraction equal fraction? It's just a nasty looking fraction equals a somewhat fraction. So, what would you do if it was this? Bless you.
You would
You'd multiply by
multiply
x.
6 by 4
Bless you.
times 10. Well, multiply each other by 60 by times 4.
Multiply by x and divide by 60.
What's that?
Wait, what do you do? Multiply each
Why is that coming up? I'm just saying, what would you do if you had to solve this? What's the shortcut for that?
Wait, divide by 4. Multiply each
Cross multiply.
Cross multiply, okay? Now, when I cross multiply this, aren't I just doing this?
4 over 60.
Aren't I just doing that? Remember if you took the long way through this, when you cross multiply, you get 4 equals 60 times x divided by 60. So you're just really just flip-flopping those two? Remember that? You don't remember the shortcut? Isn't that just, can I just flip-flop those?
That's our 2012.
If I flip-flop those, I get 50 over 40 is 1 plus 10 e to the negative 3x. Everybody okay with that? What's 50 over 40 simplified to?
5.
Okay. So that's 5/4, right? A buck and a quarter? Subtract 1. So you have a buck and a quarter, and you took away 1, how much you left with? So you got a quarter now. I'm going to put it in as a decimal. This is one of the few times that I put decimals in, just because it's easier to type in the calculator.
0.25.
Equals 10 e to the negative 3x. Divide. You got to divide by 10 first.
Yeah, divide by 10.
Because now when I divide by 10, I have 0.25 over 10 is e to the negative 3x. Now what do I do? Now you natural log it. Remember, in order to undo e, you have to natural log. So you undo e, the natural log, you're going to get the natural log of some crummy looking fraction.
That's how you check
1 over 40.
And then what do you have to do?
Divide by.
Divided by negative 3. Shoot. So again, that's just a nasty looking problem, but it's all calculator buttons. You're going to get it was a natural log of 0.25 over 10,
1 over 40.
and then I divide that by negative 3. 1.23. You guys get that? What's that?
Oh, no, then I just got you back, so never.
Again, it's straight calculator work. There's really not that much to it. Okay. Solve that one real quick. Solve that one and we'll call it a day. Everybody agree? 174?
I got a friend. Well, yeah, I'm just going right.
All right, so let's see. Section, was it 7.7 is page?
Prison. Inmate. Oh, like CI.
Yeah, I got one.
Whole whopping 11 problems. I think we'll be all right.
It just looks a lot more intimidating.
Yeah, it's
out like that.
yeah. These are 3 write the exponent function. These are 3 write the power function. 2 simple graphs and 3 solve for x. And if you guys show how fast you can solve for x on those, it's not that bad. With the minute or so that I have left here, I do want to talk briefly about there was a question on the quiz that a lot.